So this is the second lecture in the Energy Conversion Systems N course. And today we're going to go through the thermodynamics, predominantly around thermal generation, conversion, and almost everything today is about heat. Now, whilst many of the sustainable and renewable energy systems we're going to be talking about later in the course don't use heat, the present systems are dominated by heat. And this is one of the reasons we need to go through heat in a lot of great detail. The other thing is that some of the new renewable systems also use heat. So understanding what's already been done is not just important to see the present efficiencies and to understand how you might improve some of those, but also to be able to apply it to new systems in the future. So today is very much about thermodynamics. And I fully understand that there's going to be many people in this course that will have already covered thermodynamics in enormous detail. So I'm sure some people on this course will have gone into far more detail than I'm going to talk about today about thermodynamics. Today is really trying to go through the basics to allow those that have never studied thermodynamics to be able to use it for different forms of power stations and energy uses. So apologies if you already know everything I'm going to talk about today. It's really for the people that haven't done a lot of thermodynamics before this course. So what are you going to learn today? Well, the 6 key parameters for thermal power stations we're going to talk about are pressure, internal energy, volume, enthalpy, and entropy. Now, most of these, I'm sure for many people, you'll already know what they are. Perhaps if you haven't studied thermodynamics in detail, enthalpy and entropy are probably the two that need a bit more detail. We'll start from the fundamentals and actually the definition of temperature. This is something that is frequently forgotten about, but again, is really quite an essential thing that you need to have when you're looking at heat systems. We'll talk about specific heat capacities. We already used those in the first lecture to talk about storing energy in the form of heat, particularly with water or also with phase change materials. We'll go through the key laws of thermodynamics today and talk about how heat is generated, transported, and how it flows. And then really the main part of the lecture today is to talk about the key heat engines and cycles. So these are the ones that either are theoretical like Cardinal, or much more practical like Stirling, Rankine, and Brayton, which are actually used in real power stations. So we won't talk about transport and the diesel cycle, but apart from that, everything else we're using here is used in different power stations, predominantly for the generation of electricity in many parts of the world. And just a quick recap on some of the data that I showed just for the UK energy production. What I showed you is that 89% generate significant CO2. But if we look at how many of the things in here are thermal and use different forms of thermal, we're actually talking about 97% of all the energy production in the UK are based on thermal processes at present. So even if we try and reduce the dependence on particularly gas, petroleum, coal, we're still going to be using low carbon generation forms such as bioenergy and nuclear that are still dependent on thermal cycles. So even with sustainable and renewable energy sources, and nuclear, which is not sustainable or renewable, but it is a low CO2 with a long lifetime, we still will be using thermal cycles. As I said the last time, 10% of the energy comes from renewables by the European Commission definition. We went through in the last lecture why so few of those renewables are used to generate the UK's energy. And what it comes down to is when we talk about the Rankine and the Joule-Brayton schemes today, the volumes of energy and the energy density they can deliver is way above what you get from wind, hydro, and solar. And in later lectures, we'll go through these different forms of renewable and sustainable energies. We'll calculate the energy densities, and you get a much better idea what some of the problems of getting large-scale deployment of renewables and sustainable energy. Right, so thermodynamics. So we've got 6 key thermodynamic properties that we require to describe thermal power plants. So this is a picture here of a coal-fired Drax power station in the UK. So in fact, if we go back 30 years, something like 80 or 90% of electricity in the UK came from these coal-fired power stations. It's now 8% and has been reduced significantly. This particular power station has been demolished as the UK moves away from coal, predominantly towards gas systems and the dual Brayton we'll talk about today. But for any of the power stations, from coal, oil, or gas to generate electricity, we're going to be talking about temperature and multiple temperatures in the system, pressure. So we're going to have water being turned into steam, and the pressure of the gases being an important parameter in how we generate electricity. We've got the internal energy, and also today, specific in front of anything means per unit mass. So we take, for instance, if it's specific volume, we're going to use a capital V predominantly, and if we divide by the mass, this is just 1 over density. That's specific volume. Specific internal energy, we still keep a capital, but we'll talk about phase changes in a few slides and what that really means. Specific enthalpy we'll define, and entropy really is one of these parameters that was defined predominantly around heat engines and how to improve heat engines. But now in modern life, information and communications is also heavily dependent on entropy. So we'll define this and discuss how it's used in the different power plants. Now, one of the key things that you'll understand by the end of today is that if we can measure any 2 of these properties, we can determine all 6 by calculation. So in particular, some of these things are extremely difficult to measure. Entropy is extremely difficult to measure. Specific internal energy is also very difficult to measure. And enthalpy is a little bit easier, but it's still much harder than temperature, pressure, or volume. So what many of the equations we'll go through today, it will allow you to take some simple measurements of, say, the temperature, the pressure, and the volume inside a power station. And from that, you can derive everything else. And you can also derive the efficiency. So that's really what we're about today, looking at what efficiencies can we get from different thermal power stations. So the very start of thermodynamics, and in fact, it's called the zeroth law because many of the other laws were defined, and then particularly Kelvin realized, in fact, that there was no proper definition of temperature. And how temperature is defined is that if 2 systems are separately in thermal equilibrium, they're basically at the same temperature. And if we put a third one in, that must also be in thermal equilibrium. So if we have different systems in thermal equilibrium, we can make one of those systems being a thermometer, and we can get the temperature out. Now, actually, measuring a change in temperature is a relatively easy thing to do and do with very high accuracy. Measuring the absolute temperature is a much more difficult thing to do. For most of what we're going to talk about today, actually having relative temperatures is good enough to get accurate efficiencies for power stations and thermal generation. So one of the key laws we're going to use, and you'll see this law come back time and time again in what we're going through today, is Boyle's law. And this can be derived if we take a cylinder where we've got a gas at some pressure P and some volume V. Now the volume here is going to be defined by the area of the cylinder and the, the distance that this volume of gas actually takes up inside the cylinder. So just the piston area A times this distance gives us the volume. What we have in real life is that there's a force acting on this piston. If this is at atmospheric pressure, then this force should actually be at zero if it's atmospheric pressure outside as well. But in effect, the force is a pressure times an area, where the area here is the area of the cylinder. And this allows us to do work done on this gas and change the pressure and the volume. So the work done, or the incremental work done, is dW, and it's force times distance. So if the piston moves by a small amount, an incremental amount ds, s for distance here, the incremental change in work done, or energy of this gas, is the force on the cylinder times this small incremental displacement. Now, in fact, if we just look at what we've defined here, the volume that we've got, as I've said, is just the area times ds. And we can exchange in here force for PA. This is going to become the volume. So we can change this. Because we're actually pushing the piston in, we've got a negative that comes into this part of the equation, but you can see how we can derive that the incremental work done is the change in pressure, or minus the pressure times the incremental change in volume. So here's a thermodynamic differential equation that we can use, where the incremental change in work done is just minus the pressure of the system times the change in volume. Now, if the temperature is constant, then this ends up being a constant, and pressure times volume is also a constant. So dW then becomes a constant. So this...
So can you please tell me why there is a negative sign with the P?
Because the volume is decreasing.
Okay.
So because the piston is going in, this volume is decreasing. That answer your question okay?
Yeah, sir, yeah.
So this is Boyle's law. PV is a constant. We're going to use this time and time again today. But the constants, sorry, PV equals a temperature times constants. So this is how we can relate pressure, volume, and temperature. And it's for R is a constant. It's defined as 8.32 joules per Kelvin per mole. And N is the number of moles in a system. So if this is a gas, then the number of moles, 1 mole gives you 6.02 times 10 to the 23 molecules. This is known as Avogadro's number. Mole is an amount or a number of atoms that really comes from chemistry. But when it comes to this equation, this is an easy way to actually define it. So N in here really is something that allows you to determine how many atoms you physically have in a gas, or if we're working with a liquid, this also works for liquids as well. So the first law of thermodynamics is that energy is conserved in any process. And that includes where we have the conversion of energy from one form to another form. So that might be where we change heat, we do work done, or we have energy going out the system. And this, for many of the power stations we're interested in, could be electricity being produced. So we've got heat going into a system. We've got a whole series of energy conversion processes going on, dependent on the power station. And the energy coming out the system is electricity, or it could be, if this is transport, this could be kinetic energy that we have to power a vehicle. Now, in fact, for many of the thermal systems we're going to look at today, what we've got is materials that we're going to change. And the simplest one to think about here is where we change water from a liquid into a gas. So water as a liquid, if we heat up, we get at atmospheric pressure to 100 degrees C, it becomes steam and it changes into a gas. Now later in this lecture, we'll actually go through that process in much more detail about the thermodynamics, but there will be some change in internal energy in the system. This is something that James Black actually discovered at the University of Glasgow a number of centuries ago. And the key thing here is that the input energy Q minus the energy or work done by the system minus W equals the internal energy change in the system at delta U. So overall, in any thermodynamic system, energy is conserved. But we need to draw a boundary around the system, and we can have energy changing or different processes going on inside that total system. So sometimes historically where people have claimed that they've managed to generate additional work done in greater than 100% efficiency in systems, that's because they haven't drawn the boundary of the system large enough to be able to have energy overall conserved. And that frequently is the problem when people are claiming perpetual motion machines or where they have 100% efficiency in a system. We'll talk a little bit later in this lecture about the efficiencies in detail and why you can never get 100% efficient systems. Now, what I should also say here is there's a convention that if heat is going into the system and work is being taken out of the system, then Q and W are positive. And so we still have this Q minus W equals delta U. You may see in some textbooks or some other lecture courses that these can be defined in different directions, and you might get a change in this negative sign to a positive, just dependent on the energy and heat flows that are defined for that particular equation. We can also look at the incremental values here, and we can have dq minus W equals the change in internal energy. So here we're just looking at incremental changes, and we're still getting the same overall work done going out of the system. So energy being conserved is something that the majority, well, I'm sure every student in this course understands that and has previously seen it in other courses. Enthalpy is something that was actually originally derived for the study of heat engines, and particularly for using steam engines to generate the maximum power. And enthalpy is defined as the internal energy plus the pressure times the volume of a closed system. So if we look at a steam engine where we've got water and steam in a system, the input enthalpy of the system, sorry, the output enthalpy of the system minus the input enthalpy equals the heat that we actually put into the system. And you can maybe now understand why this was defined for the study of steam engines, because we get a very simple equation here that the output enthalpy minus the input enthalpy of the water and steam in the system is equal to the heat that we've actually put into the system to turn the water into steam. So what's going on when we do this is basically Q here is being used as the latent heat of the phase change to turn the water into steam. And it makes a very simple equation that can be used in a lot of different steam engines. So just to show a little bit more, we need to also talk about adiabatic systems. And this will become important when we talk about the different power stations and thermal cycles. So adiabatic is where there's no heat input in the system. Now, in reality, for all the systems we're going to talk about today and the adiabatic processes that go on, in reality, there's probably always going to be some heat input or output. So a negative in here for the heat still, well, strictly speaking, means it's not adiabatic. But we're going to assume the systems are effectively adiabatic to make it simpler to do calculations and to understand the thermodynamics of each system. So what we're doing in thermodynamics throughout this lecture and this course is we're assuming an ideal system that where we talk about adiabatic processes, yes, there may be small amounts of heat change in those adiabatic processes, but for the sake of the calculations and the understanding of the thermodynamics, we assume that it's a perfect system, that there is no heat input or output. So if we look at a turbine where we've got steam going in to turn the turbine and allow work done to be extracted, we've got an input pressure and an input enthalpy, an output pressure and an output enthalpy. And what we can show is that the work done that we get out of this turbine is the input enthalpy minus the output enthalpy. Now, this only is the case if there's no heat changes in the particular system. And you can see that since the enthalpy is just the internal energy plus the pressure times the volume, the work done that we have here is a change in either the internal energy, the pressure, or the volume of the system. So specific heat capacity. So we use specific heat capacity to allow us to understand how much energy can be stored in a thermal heat storing system in the last lecture. More generally, what specific heat capacity is defined as, it's the rate of change of heat with temperature, but where we actually have to have a restriction on the system. So we can work out the specific heat capacity for constant pressure or for constant volume. There's a few other constants you can potentially put in there, but for all the systems we're going to look at, we're going to either be talking about constant pressure or constant volume. So if we look at constant volume first, the specific heat capacity at constant volume is the rate of change of heat with temperature at constant volume. Now, at constant volume from the first law of thermodynamics, we've got heat minus work done equals the internal energy. But in this particular system, what we have is that the work done at constant volume is 0. So the heat that we have is just equal to the internal energy U, and dQ equals du. So in fact, CV also equals du by dt at constant volume. If we look at the specific heat capacity at constant pressure, well, we've got the same rate of change of heat with temperature at constant pressure. This time, what we can use is that the enthalpy in the system is U plus PV, but since we're at constant pressure, that's the enthalpy is just the heat Q. So we can rewrite Q as U plus PV. So then if we differentiate, we have the rate of change of the internal energy with temperature at constant pressure. Well, we're at constant pressure, so we don't need to differentiate that. But we then have to differentiate the volume with temperature at constant pressure. Now, in fact, this is just the same as the rate of change of enthalpy, because at constant pressure, the heat just equals enthalpy. And so in fact, dQ by dt is the same as dH by dt for constant pressure. So there's a few tricks in here that are used from the fundamentals of thermodynamics. These things can become useful when you're actually analyzing power stations, as we'll do later in this lecture. Now, the equation that we used in the last lecture was this: heat as energy equals the mass times the specific heat capacity at constant volume times the change in temperature. This just comes from this equation after integrating it up. And we have to multiply by the mass, because specific heat capacity, if we want to get the absolute value of heat, we need to multiply this up to get the absolute rather than the specific heat capacity. So this is how we get this equation. It just comes from integrating the specific heat capacity and dq by dt, a constant volume. Okay, so one of the other definitions that we need to understand, now we're not going to use this physically in the power stations and the efficiencies, but it's very important in a number of the systems where we look at practical ways, either of renewable energies or the practical way of designing power stations using fossil fuels and thermal processes. So it's Fourier's law of heat conduction. And if we have a material that has thermal conductivity kappa, we have, in this case, we're looking at just a leg where the material has an area A, and the heat is going to flow through this material. Now, in this course, I'm always going to use Q and heat as energy, but Fourier's law really defines heat in terms of power. And what you may see in a lot of textbooks or some other lecture courses is that frequently Q is intermixed, and sometimes it's used as energy, sometimes it's used as power. And in fact, in some textbooks, it's used for both, which I certainly believe is very confusing for many students and even for teachers for that matter. So here I'm going to be explicit that Q is the energy and we need to divide by T to get power. And as you can see here, what Fourier defined is that we have thermal conductivity times area. And there's a historical aspect here that relates to Kelvin and one of Kelvin's papers from the 1840s. Now, this is before the second law of thermodynamics. Fourier came up with this law. And at the time, nobody understood in which direction heat moved. But to be consistent, we put a negative sign in here, and we have the cold side T1 minus the hot side T2. We divide this by the length, and for a one-dimensional system, this basically is Fourier's law of heat conduction. So you'll sometimes see this equation rewritten without the negative sign at the start, but with T2 minus T1. Both are correct, but in fact, this is the one that when we also come to efficiency of thermoelectrics and energy harvesting systems will become quite important for the flow of energy having a negative at the start. So don't worry about this too much at the moment, but it's negative, so heat flow is positive when we're going from a hot to a cold side. So basically, when we abide by the second law of thermodynamics, as you'll see later, we need to have the negative sign in here in T1 minus T2. Now, this is one-dimensional, and it's nice and easy to understand in a system. More generally, Fourier's law is typically written with nabla T in here. And this just allows you to expand to 3 dimensions and all directions. So if we use Cartesian coordinates, nabla T is just dt by dx along the x direction, dt by dy along the y direction, dt by dz along the z direction. So you could actually exchange this for spherical coordinates, cylindrical coordinates, or any other geometrical coordinate system you might want to use that's appropriate for whatever application you're using the equation. But most of this course, we're just going to keep it nice and simple with one dimension, and this reduces down to T1 minus T2 divided by the length when we look at one-dimensional heat transport. So here's a very simple example of this. And what we're thinking about is a hot sink at 500 degrees C. We've got a cold sink at 20 degrees C. And we're going to assume that these are thermally massive enough that they keep the same temperatures when heat is flowing out of the hot side and flowing into the cold side. So a question for everybody here is, if this is an area of 1 square centimeter, the material has a thermal conductivity of 150 watts per meter Kelvin, and it has a length of 1 meter, how much power is actually flowing through this rod. So has anybody got an idea, if we go through Fourier's equation, how much power, so heat per second, are we going to get flowing into the cold sink on the left-hand side?
2.2608 times 10 to minus 3 power to minus 3.
No. Anybody else?
I got like minus 70, or sorry, 72,000. Is that right?
No.
Oh, damn.
There's a 7 and a 2 in the answer, but you'll see where you've made a mistake, and it's a common mistake, and it's why I'm doing this example.
Is it 720?
No.
73500.
No.
Is it because it's meant to be in Kelvin? Oh no, because it's a difference in temperature, so that shouldn't matter. Never mind.
That's correct. Right, let me go through it.
Squared.
Okay, somebody on the chat has got the correct answer at 7.2 watts. So let me show you, and I've deliberately done this, and maybe perhaps a little bit obnoxious, but it's a real problem when you work in energy, because when you go and look at textbooks or you look at problems, you've got many different units here. So the first thing to note is I've given you 1 square centimeter, and to be able to do this with 1 meter length, to have area and length, they have to be in the same units. So you need to change area into meters, and so that's 10 to the minus 4 square meters. So if we now have the minus 150 watts per meter Kelvin, we've got 10 to the minus 4 for the area, and we've got 20 minus 500 in here. And hopefully, if I haven't done anything wrong with the calculator, you end up with 7.2 watts. So I know once you've seen the answer here, it's quite simple, but it really this is really something you need to worry about when you look at all the energy systems, because frequently the numbers are all in different units and you have to get everything into the same units.
But the temperature given in the Celsius, so we have to convert it into the Kelvin scale, na?
Well, here, because it's a difference between two numbers, if you convert it into Kelvin, you're adding 273 onto both of these numbers and subtracting, they subtract to 0. So if you're taking a difference, it doesn't actually matter if you convert it into Kelvin. However, if you're looking at something where it's absolute temperature, so for instance, if we look at, for some of the thermodynamic relationships, so if it's PV equals nRT, T in that case you have to do in Kelvin, because it's the only way it matches with the rest of that equation. So somebody else is asking why the negative is here. 150 is not negative, it's the equation has a negative in here because it's T1 minus T2. And that was simply because of the direction of the energy flow and making this equation agree with the second law of thermodynamics. So you can see that, you know, this should be quite an easy thing to do. Now, I know it's difficult when people are doing things in front of a class and in front of people and pressure gets on, but you know that you can see how many or how easy it is to make mistakes in this sort of calculation. So that's for conduction through a solid material. That doesn't happen instantaneously. Now, for a lot of the things we do in this course, it's not going to matter too much, but you have to understand that if you start or change the temperature on one side, it's not instantaneous that the heat flows the whole way through the system. And in fact, it takes a finite amount of time just to establish a steady state or get to an equilibrium heat flow. And you get, or you can do a very simple back of the envelope calculation and approximation to actually work out the time or the finite time to establish that steady state or equilibrium heat flow. And I'm not going to derive it, but it's given the time is given by the distance squared times the density of the material times the specific heat capacity of the material at constant pressure divided by the thermal conductivity. And sometimes this is written in terms of alpha, where alpha is known as the thermal diffusivity, and alpha is just defined as the thermal conductivity divided by the density times the specific heat capacity at constant pressure. So this is here more just to say that, you know, when heat flows and heat starts flowing, the processes are not instantaneous. And in some systems, particularly with a delta T, it can be, or the distances can be quite long. You really have to start worrying about the time it takes to get to steady heat flow. So the other area that we'll actually use in a number of renewable and non-renewable systems is convection. And this is typically where we think about the bulk motion of a fluid. Now, when I talk about a fluid, that could be a liquid, but also a lot of the time we'll look at the flow of gases. And that can just be the air. It might be other gases in a particular system. But if we consider the gas and the liquid as being incompressible, that's typically what we're going to do. And then we can have a mass flow per unit area per second, which is just the density times the velocity of that fluid moving through a pipe. So we're going to be interested in a number of systems where the fluid in the pipe is going to transport heat. Typically, you can think about maybe a ground source heat pump where we pass water through the ground and we want a liquid to carry heat that we can then use in a house or in a building or somewhere that is of value. So the thermal energy per unit mass we've got is going to be the specific heat capacity at constant pressure times the temperature. And so a rate of flow of thermal energy by convection through this pipe is going to be, well, what we're doing here, it's the heat energy divided by the area of the pipe is the density of that liquid times the speed. So this is just the mass flow per unit second, per unit area per second, times the specific heat capacity times the temperature. So you can see here in this particular equation, it's going to be Kelvin that you need to use for the temperature. Sometimes you'll see this equation with the area up on the other side. I've put it down here because a lot of the time in power stations, it's the power that you're in, it's the power or energy density that you're actually interested in as well. So here it's energy density, but you can move the area onto the other side of the equation. So this stage, I'm going to have a quick break. I'm happy to take some questions. We'll just stop the recording. If I can get the right